A good code, right? What is actually meant by a good code? What all parameters that a good code need? What is readability? And we started discussing about scalability. Am I correct?
Yes, sir.
Yes. So to understand scalability, we are writing this code. So we just developed this. We declared a string here, and we try to here this loop is to assign some values to the array that we have declared, and this loop is to find a string in that array, and then we are trying to find the differences in the time. We are capturing the time before starting this operation, and we also captured the time once we have done our operations, and then we are trying to get the difference between the times. So the whole intention is scalability is something up to what extent we can scale our code, up to what number of inputs we can extend our code, so that uh, as the number of inputs are getting increased, our code should not execute for long time. That is the whole concept. So when the inputs are increasing and the time of a code is increasing, it's not a good criteria. I mean to say, even if the number of inputs are getting increased, it should not get slowed. Like, I don't say like it will not get slowed. It can slow, but it should not be a very drastic change. So a good code should always maintain that criteria. So even the input criteria is keep on increasing, it should maintain a time span, or it should not increase the time span drastically. So that kind of code can be said as a good code. So in this case, I'm just demonstrating that. So here, I'm just trying to show you the how the time is changing if the inputs are changing. So I'll try to capture here the time difference between the before time difference to execute these operations, and now I'll keep on increasing this array size, and I'll show you the outputs, so you can see how much this time is varying when the inputs are varying. So here I'm taking the sys out, and I'm just converting into nanos. You might know nanos is 10 to the power of minus 9. So this is my code. Now what I am doing is I declared an array, and I want to assign some values into this array. So this is my array, and I want to assign some values to this array. So to index of 0, I'm assigning our required value, and I'm saving this. So let's say this is my code. What I'm doing, I declared a string and assigned the apex value, and I'm also iterating through the entire string array, and I'm assigning some values, and then I'm coming down, and in this loop I'm checking for that value. So I'm taking the time that is being taken to execute this particular code. So if I run this code, it is taking me 0 nanoseconds to execute this. So let me increase the size of this array. So instead of 100, we scale this to 1000 elements. So if I run this code again, so now it is some more time. Let me convert this to uh, microseconds, or I mean to say, let's convert this to milliseconds. Math dot power of 10 to the power of minus 6. So let it be this. So this is coming as nanos, and I'm converting that to my milliseconds by multiplying that with 10 to the power of minus 6. So that will be readable sense. So this is a huge number, we will not be able to understand this. So run as Java application. So now it is 1 millisecond to execute this code which has 1000 elements. Now let me increase this to 10,000 elements and check the time how much it is taking. So run as Java application. Why it is 0? So it is taking somewhere around again 0.9 milliseconds. If I run this again, it's taking me the same time. Let me increase this. So let me put this as -3. So instead of milli, I'm taking it as micro because it gives you a sense like the change will be more. So it is 4025 when it is 1 lakh elements, and let's change this to 10,000 elements and let's check the output. So the execution time here is 1044. If I increase it to 1 lakh, so now the output will be around 5983. So let me put it on notepad. So for 10,000 elements, the execution time is 10,000 elements. The execution time is, let's come from here, run as Java application. So for 1000 elements, it is 997, right? So let me put it here quickly. So for 1000, it is 997, and for 10,000 elements, what is the time it is taking? It is the same 997.7. For 10,000, 997.7. So for 1 lakh elements or for 1 lakh inputs, so the execution time here is 4954. There is something wrong with my paint. So but now you see, when we keep on increasing the changes, what is happening? So the time is drastically increasing. So now it is taking 19,000 from 4,000. So if I keep on increasing this, so the time is increasing drastically. From 19,000, it switched to 93,854. So as the number of inputs are increasing, so the execution time is drastically increasing. This says that so now, based on this criteria, we can judge whether this is a good code or not. So if instead of, if you change the logic of this, and if you're able to find it something, if for the same number of elements, if you're getting this executed in 19,000 microseconds or something, then we can say it as a good code, right? So the execution time is less when, even if the input count is increasing. So that kind of code can be said as good code, and if we can compare based on this. So I'm doing the same logic with two codes, and one code is executing is 90 in 93 microseconds, and the other code is, let's say, it is executing is 19 microseconds. Then we can decide the other code is the best code when compared to this code, right? So this is one of the criterias that is used to know whether a code is a better code or not. So we call this as time complexity. So time complexity is something which says us in what, it calculates the time. It calculates the rough time in which a code will get executed or something. So that is the whole concept here. So this is an example showing when the time is, when the number of input criterias are increasing, or the number of inputs are increasing, or when we are scaling the input, the number of the time that is taking to execute this particular code is increasing drastically. So if someone can develop a code which will execute in very less time, even if we are scaling the inputs, then we can say the code is executing in very less time. I mean to say, it has very less time complexity, and it's a better code. So for that, we have a notation called as big O, that is used to calculate these kind of time complexities. So big O is a notation that is referenced to say what is the time complexity for a particular code. And now let's see what is what is big O notation, and how do we calculate that big O notation for a particular code. So before that, let me remove everything. So I have a string array of length 100. Let's say now I have a string array of length 100. And now what I'll do is, I'll just sys out names array of 0. Control C, Control V, and 0. This should be my output. And now I'll assign some value to this. For 0th index, I'm assigning a value called as suffix. Okay. So the requirement is given like this: you need to have an array, and from that array you need to print out the first index element out of this array. That is the code requirement that is given to you. So that is the requirement given to you. Now can you say me the time complexity of this? If you look at this code, it can be any number of strings, but we are just printing only the first element of this array, or the element at 0 index is being displayed here. So if you consider this, so now if I run this, it will take the same time. Even if I increase this to 1000 elements, it will take the same time. So even if you increase it to n number of elements, it will take the same time, because we don't consider the array size here, because we are just bothered about only the first indexed element in this particular array. Am I right or not? So whatever can be the input, it will just print out the first element in that array. So we can call this as constant time, because even if it is n number of elements, we are just printing only the element at index 0. So if you take this graph, or let me put this in graph. So let's say I have inputs of number 1. If I have one input, the output, let's say it is taking us 1 second to execute this code, right? If you are taking 2 seconds, it is executing it in 2 seconds. I mean, it will take 1 second for the execution. If you're giving three inputs, if the input is 3, the code is taking 1 second. So the input can be n numbers. So we can have n number of elements in the array, but still it takes only 1 second for the execution, right? If you put in this graph, if you keep this in graph, how the graph looks. So let me open an online board, that would be easy, I feel, instead of this paint. So this is my x-axis, and here I have the number of elements. So here it is number of elements. Can I write something? So let's say this is my x-axis, and x-axis has number of inputs, and let's take the y-axis, and the y-axis is the time taken to execute our code. So it is time to execute our code. Now if you mark the values, how it will be like, if it is if it is one element here, if I have one element, what is the execution time? It is 1 second. Even if I have two elements, the execution time is 1 second. So this is the point, intersection point for both of them. So for one element, the execution time is 1 second, and for two elements, the execution time is 2 seconds. For five elements, the execution time is 1 second. So even if it is n number of elements, the execution time is 1 second, right? So if you draw a graph joining all these points, it is a constant line. So this graph says us, even like these kind of codes says that even if we have n number of elements, or even if we scale to as many as inputs that we want, but the time complexity graph is constant. So it is just taking us only 1 second or n seconds to execute this particular piece of code, even if we have n number of inputs, or even if we scale our code to as many number of inputs as we want. So these kind of graphs are called as constant time complexity graphs. So these graphs are called as constant time complexity graphs. So let's take another code and let me show you the other example. So let us loop something like this. So I hope everyone understood this time complexity graph, right? Constant
Yes,
time
sir.
complexity graph. So the other graph is, let me take an array, I mean for loop, and let me initialize this with I is equal to 0, I less than named array dot length and I plus plus. So inside this I'll try to assign the values into an array. So this is my array, and inside this array I'm just trying to add some values to this. Let me say it as a. So let's take this code and put it as, let's keep this as an array of length 2, and inside this array uh, I'm assigning 0th index with one value, and then I started iterating from 1 to the length of array, and I'm assigning some values into this array. So this is the code. Let me remove this as well. Instead I'm iterating it from 0 to length of the array. So let's say I have two elements in I have my length of the array as 2. Now can you say me how many times this loop will iterate to store the values into that array?
Twice.
Two times, right? So if my input is,
Two times.
right, if my input is 1, it will the loop will iterate for one time. If my input is 2, the loop will iterate for two times. So if it is 3, what will be the loop will iterate for three times. So it can be n number of elements. If we scale our input to n number of times, n number of elements, so the loop will iterate for n times, right? So let's say for each iteration it is taking us 1 second. So for two iterations it will take us 2 seconds. For three iterations it will take us 3 seconds, and for n iterations it will take us n seconds. So if you draw a graph for this kind of codes, it will look like this. So again I'm taking a graph. So on x-axis we have number of inputs, and on y-axis we will spot time to execute values. So for 1 second, let's say it is, if the number of elements is 1, it is taking us 1 second, and for two elements it is taking us 2 seconds, and for three elements it is taking us 3 seconds, and for n elements it is taking us n seconds. So if you join all these points, it is linear, right? So whenever the number of inputs are increasing, and if the time is getting increased in a linear fashion, we call that as linear time complexity graphs. So this is constant time complexity graph. Why? Because even if we are scaling the inputs to n, the time is same. It is still pertaining to or consisting itself to 1 second. But here it is not the case. So it is changing the time is also getting changed in a linear fashion. If you are increasing the inputs drastic, I mean in a linear fashion, so the output, the time is also increasing in a linear fashion. So it is a linear graph. If you draw the graph for these values, it's a linear graph, and we call this as linear time complexity graph. So this is called as linear time complexity graph. This is how one can predict the time, I mean scalability of a particular code. So if you can predict, you can scale the, you can take some sample inputs, and then you can take the number of time that is taking to execute that, and we can plot a graph, and we can call that as time complexity graph for different code criterias. But here if you consider, so let's say this will also take some time to get executed, right? So this will actually take time, and this initialization will also take time, and we are comparing something here, and then we are coming here. So if to say it precisely, so let's say this is taking 1 second, and this takes 1 second, and let's say this takes 1 second. This initialization is taking 1 second, and assigning value is taking 1 second, and this incrementing is this increment is taking 1 second. So the total execution time of this is 1 second for one iteration. So for the other iteration, it can take 8 seconds. For the next iteration, it can take 12 seconds, but still it should be a linear graph. It is just moving upwards, but it should be a linear graph. So instead of 1, it will move to 4. Instead of 2, it will move to 8. So this linear graph will move upwards, but it will be a linear graph. I mean to say it's a constant, it will have a constant slope. So that is how we can draw time complexity graphs for different kinds of codes. Before that, let me tell you what is big O notation. So basically we have something called as big O notation, which is used to calculate the time complexities or space complexities. Time complexity is something which says us how much time it is taking for the code to get executed. In the similar fashion, we have something called as space complexity, which says us how much space our code is occupying. For example, if you take this code, we have only one thing that we are storing. We have a variable that we have initialized, and we are storing some value into it. So there is, apart from this, we don't have any other things that we are storing here. You consider this as an input, and this we should not consider the inputs as storing parameters or something that your code has to handle the space, because inputs are something that are being given by the users, and you don't have control on that. So user can select it as 3 inputs or n number of inputs. It's in the user's hand. So that is the reason we will not consider the input criteria when we are calculating the space complexities. Space complexities are being calculated only for the variables or strings or arrays, whatever it can be, whatever the storage that you are doing. You need to consider those parameters only. So for this particular code, or for this particular logic that we have developed, the criteria that is given here is, you need to assign the values into the array. So to develop that piece of code, you used only one variable, that is I, and you're storing some value into it. So the space complexity has to be calculated only for this particular statement. Other than this, we are nowhere using the space, I mean we are nowhere storing anything to our space. We are using the array that is being given by the user, and we are just assigning some values. These are all math operations that we are doing, but this is the storage. But when we are coming to calculating the space complexity, we need to consider only this. When we are coming to time complexity, we need to see how many inputs are there and how many times this loop is iterating. So using those criteria, we can calculate the time complexity, whereas when calculating the space complexity, we just need to consider only this particular parameter. So that is what space and time complexity is. And let's take multiple inputs, and let me show you what is big O. So big O is something that is used to show or that is used to display the time complexity and space complexities, and it is basically denoted like this. So it's big O, and inside this we will mention the uh, kind of graphs. If it is a constant graph, we can say it as C. If it is a linear graph, we can say it as N, because linear graph is something called as N. If you remember, for linear things, for linear kind of graphs, we have an equation called as y is equal to mx plus c. C is a constant and m is the slope of that particular linear line, and so those are constants. You can also mention like this, mn plus c for linear graphs. But we have few rules for this big O notation. When we are writing big O notation, we have few rules that needs to be followed. So one of the rules is you need to exclude all the constants and dominant parameters only has to be there. So if you see, this is the equation for a linear graph, right? Let me put like this, mn plus c. So this is the graph for the linear graph. This is the big O notation for the linear graph, let's say. So one of the rules is we need to exclude the constants. We need to exclude the constant when we are writing the big O notation. And the second parameter is we need to keep only the dominant parameters. These are some of the rules when we are writing the big O notation. The first one says we need to exclude the constants. Why? Because let's say now the input is let's take an example here. Let's say my slope is 2 and n, and my constant here is 3. Okay, so this is my equation, or the time complexity equation I have. Let's say my input is 1. If my n is 1, this is dominant, like 3 is dominant. So but I cannot say my n will be 1 always. If it is 10,000, is 3 not very small in when we compare this to 10,000? Or if it is 1 million, or if it is 10 millions, as n is growing and growing, the 3 will be less predominant in when we write that with n, right? So this will not be so dominant when when we are increasing the size of the input drastically. If it is 2 millions, the 3 is very small when compared to 2 millions. So that is the reason we can neglect this. In the similar manner, even if you multiply that, if even if you multiply an infinity inputs to into 2, it will be an infinite, right? So even then you can simplify this. You can even then you can remove this 2 as well, multiplication factor 2 as well. So if you consider n as infinity, and if you multiply that with 2, again the output value will be infinity. So that is the reason. So when the inputs are growing very high, you doesn't need to consider the constants or multiplication factors, and you can remove all of them, and you can keep only the n that is there in the equation. So based on these two rules that are given to calculate the big O notation, we can conclude the big O notation or the time complexity factor for this particular equation, or for this particular piece of code, is n. Got this?
Yes, sir.
So that is how we can calculate the time complexity factor for this. So if I take this example, and now the other example, other code. Now we are assigning some values to it, and now we are trying to fetch the values from that array. We are trying to find out some array into 0. I is equal to 0. I less than. So now let's try to calculate the time complexity of this. Oh, what is the time complexity for this? It will be a constant time complexity, right? So because even if the number of inputs is increasing, declaring an array is something which will take us a constant time complexity. So let me call this as O of C, as this is constant time complexity. So can you say me what is the time complexity for this?
O of 1.
Big O-N.
N square.
O
N.
1. It's the first element, so it is 1.
Yeah,
There
it
are
is.
two for loops, that's why O(n) square.
We can say this as a constant parameter, constant time complexity, right? So let me, instead of 1, I'm putting it as C again. So or else some other variable. So for this, what will be the time complexity for this particular loop?
It is 2. So we can say O of n.
Yeah, this is O of n, right? So then what is the time complexity for this particular loop?
The same O of n.
Right, it is O of n. So if you sum up all the time complexities, what we are getting, it is C plus A plus n plus n, right? So again, if I sum up C plus A plus 2n is the time complexity. According to our rules, we can exclude these constants, and we can also exclude the multiplication factors or denominators or division factors, and finally we can come up with something called as n. So the time complexity for this whole code, we can say it as order of n, right? Am I right? Can we say the time complexity of this whole code as order of n?
Yes, sir.
Yes. So based on the rules,
Yes,
we
sir.
excluded the constants, and we also excluded the multiplication factors, and then we ended up with something called as n, which is the time complexity for this particular code. So you can easily visualize that as the number of inputs are increasing, C and A will not be dominant, and multiplication doesn't matter. So we excluded all those parameters or all those constants, and we come up with n, which is the time complexity for this particular code. So this is how one can calculate the time complexity of this. So can you say me what is the space complexity for this?
O1.
Yeah, it will be constant space complexity, because we have a single variable that we have here that we are initializing, or for this variable itself we are using the space. So let's say if the space complexity of this is O of constant some C, or else it can be A, and for this particular variable we are reassigning it and we are storing it. So let's say it is O of A. So the space complexity will be constant space complexity. So A plus A will be 2A, or you can also replace this with n plus n will be 2n, and we can remove 2, and the says sorry, this is constant, it is not n. So C, it is C, and let's say this is A or C, it can be anything. So 2 C plus C, two constants, adding two constants, so you can say something like A plus C is the space complexity. Or else if the space complexity for both the variable initialization is same, so if you say C plus C, it will be 2C, and we can you can remove 2, and you can say that as constant space complexity. So C plus C, 2C doesn't matter. If C is 1, it will be in the first line. I mean, if the y-axis will be equal to 1, if it is 2C, the graph will be moved little up. So it looks something like this. So if it is C, it will be like this. If it is 2C, the graph will move upwards and it will be like this. So but still then it is a constant space complexity graph. So that is the space complexity for this particular code. So we can say the space complexity is a constant space complexity, and the time complexity for this particular code is linear time complexity graph. Hope everyone got this right.
Yes.
So if you consider this case, what is the worst case of this case and what is the best case? So what we are doing, we are initializing an array, and in that array we are trying to find a string, right? So let's say I have an array of 10 elements, or a size of 10 or index of 10, and inside that array I have multiple elements. So in that particular number of n number of elements, I am trying to find out a string which is called as apex. And what is the best case and what is the worst case that you can say for this particular code? So when the number of
The
iterations will be
best,
increased, so the minimal number of iterations that we do, that we call as best index, I mean best case. If the number of iterations are very bad, we can call that as worst case, right? So when we will do less number of iterations in this case?
So the best case scenario is like the zeroth element, so it's O of 1. The worst case scenario is the last element, so it's O of n.
That's right. Great. So the best case is if the string that we are searching for is at 0th index, so we can leave iterating the rest of the elements, like, or n minus 2 times. We doesn't need to iterate for other n minus 2 times. So we just need to iterate for only one time, which is the best case. So if it is, let's say, if this apex string is there at the length array dot length minus 1, or it is, if it is at the last index, we need to iterate we need to iterate all the times, like array length dot I mean array dot length minus 1 times we need to iterate for this, iterate to fetch that array or string. So that is the worst case. So whenever we are calculating the big O notation, you need to always consider the worst case, and you should not go for best case. Let's say if I'm taking the best case and I say the complexity of this, or the time complexity of this particular code is O of constant, uh, it's not the right calculation. So let's say if the apex is found at index 0, and if it is throwing, if it is taking, if even if you increasing or scaling the input array, if it is taking, if it is iterating for only one time, and if you're saying it as constant time complexity because the loop is executing for only one time, it's not the right calculation. So that is what all I mean to say. So if you're taking the best case, the time complexity will be a constant time complexity, but if you're taking the worst case, the time complexity will be linear time complexity. So whenever you're calculating the big O notation, you always need to consider the worst case. That is one of the conditions that are, or one of the rules that are provided. You can exclude the dominant factors is one thing, and also you need to consider the worst case when we are when you are calculating the big O notation. This is one of the rules, or the thumb rules that we have when when we are calculating the big O notation. So this is all about calculating the big O time complexity and space complexity for a particular code. And we also have something like,
Mohan, I have a question.
yeah,
So usually these comes only for search and sorting, right? So do we have to consider this for like inputting like data too, or it's only for sorting and searching we do the big O notation?
we can it's not constrained to searching and sorting. So it can be any kind of code, it can be any kind of algorithm, right? So whatever code that you have developed, it can also be developed in another way. Am I
Oh,
right?
okay.
So it can be
Okay.
anything that you develop, but to decide which code is the better code, and you can scale up to what extent you can scale that. And so you cannot load it for some hours and hours, right? So if the something that you have developed has to load in a maximum of 5 minutes, so if it is exceeding the 5 minutes, you cannot consider that code for the deployment. So you need to exclude those kind of codes, and you need to think of the or rewrite the code that is taking more than 5 minutes, even if you are scaling it to very large input. So in that case, it can be any kind of code, but the only consideration that you need to take is you need to calculate the big O notation for them, and then you need to decide which has to be deployed and which has to be neglected. So it's applicable
Oh,
for
okay.
any single logic or whatever logic that you have developed. You can apply this for them. It's not constrained to any sorting or searching
Okay.
itself, but you can do it for everything. So we have something called as big O complexity chart.
Okay. Thank you.
So here you can see something.
Sir, I have also one question.
Yes.
So space complexity we calculate only for the local variables like that. We don't count for that instance variable.
No, no, no. It's not like that. So I don't consider that as instance variable. In our case, the outer array that we have declared is not something like instant. You shouldn't consider that as instance variable. You consider that as an input. It is the user input, right? So the user has given a question like this: I have an array with me, and you find
Yeah.
out the element, I mean the suitable element in that array. That is the logic that is given to you. So if you consider this particular question from the user, so what is the input here? The string array of string is the input, right?
Yes, sir. Hmm.
So that is the user input. So for user inputs, we don't consider this calculating the space complexity. Whatever logic that is being developed for the user requirement, we consider that we need to consider only that piece of code to calculate the space complexity. We excluded this particular string array not because this is instance. This is because this is an user input. This is the user input that is given by the user. It can be any number of elements. Tomorrow he can add 5 more elements for this, and in this array of 7 elements he wants to fetch us this apex string. So this should be our logic, and this should be our input. So that is the reason why I haven't calculated this particular array. This is a storage parameter, but still I haven't calculated this because this is user input. For user inputs, we don't consider calculating the space complexity. Other than that, we will consider every storage in our particular code for calculating the space complexity,
Okay, sir.
right? So just exclude the user parameters or user inputs, and rest all you need to consider calculating the space complexity for whatever storages that you're using. So if you see this graph, this is the big O notation graph or chart, big O complexity chart we call this. So this is right. So here you can see all the reds are horrible and yellows are bad, and this is fair, good, and excellent. So 0 of 1 is a constant time complexity graph. In the similar way, we have a linear time complexity graph, we have logarithmic time constants, we have factorial time constants, big O notation of 2 to the power of n to the power of 2, or n square. We have different complexities. You have a requirement that is given for you, and one person has developed a code with a time complexity of order of n, and the other developed this with order of n square. So which code has to be considered can be decided based on the time complexity. If it has order f1, this is the best code that needs to be developed. If it is order of n square, that is horrible code. We cannot scale it to as much as we need. So we can scale these kind of codes only to certain inputs, and which will not be valid in the real case scenarios. So if Google constrains the number of actions on its browsers to limited numbers, so it will be horrible. It might not have become that much popular, as it has taken care of this time complexity in each and every algorithm that it has developed. So it became popular. So for any kind of algorithm or code to be uh, to be successful, it should have minimal time complexity. So that is one parameter that we can say, because it will get executed in less amount of time. And coming to the space complexity, nowadays space doesn't matters. So we have huge amount of space that can be created or that can be used. So time complexity is something that user experiences. So if the code is taking very long time to, or if some website is getting very high time to load its content onto the web, so it creates a bad experience for the user. It doesn't The user doesn't it doesn't matters to the user how much space that the code is using, but the only consideration that he takes is how much space, how much time that the code is loading or the web page is loading is what he considers, and that can be achieved with time complexity. So a better code can be something like, if it has better big O notation, we cannot say that as a good code. It should have readability as well, and it should have the better big time complexity and the space complexity. Let's say if both of the codes, if we have two codes and one code has better time complexity, let's say both the codes has same time complexity and one code has huge space complexity and the other code has less space complexity, then which is the better? So the one which has less space complexity and one which has low time complexity is the better code. So this way we can calculate, we can evaluate which code is the better code based on the time complexity and the space complexity, and we denote this time complexity and space complexity with a big O notation, which is denoted by this O, big O. So this is what time complexity and space complexity is. So hope everyone understood this. What is time complexity and how what is space complexity, and if you're scaling the inputs, how the time is changing. With a simple example, we have seen that. And also uh, we tried calculating the time complexity and space complexity for simple codes, and now I recommend you to take some sample codes that you have already been developed and try to calculate the time complexity. And you also try to reduce the time complexity. If the time complexity of the code that you have already developed for your Selenium codes or something is order of n square, if you're using two loops one inside the other, it will be order of n square. So if you take like this, if I have some other code like this, for int j is equal to 0, 0 j less than names array dot length and I plus plus names array of dot length j plus plus. Can you say me what is the time complexity of this?
O of n square.
Yes, O of n square is the time complexity, because we are
O n
iterating.
square.
Yes, correct. So we are iterating the inner loop 10 times and we are also iterating the outer loop for n times. So we should multiply. So it will be n into n. For two inputs, we are iterating 4 times. For 4 inputs, we are iterating 16 times. So it is the square. So the order of this particular code, or the time complexity of this particular code, is O of n square. So if you have codes like O of n square, you try to implement that with the time complexity of O of n, which is a better code when compared to a code with order of n square, right? So if you have something like that, you try to re-implement the code that you have already written with lesser time complexity, so that it can be scaled to huge amount of inputs and it will be faster as well. So you just try to calculate the time complexity and space complexity for the codes that you have already been developed, and you also try to fetch the ways if the time complexity or space complexity can be reduced by rethinking the logic that you have already been developed. So this is something that you can do once you know about this time complexity and space complexity. And now let's switch to something called as recursion. Do anyone of know what is recursion means? What is recursive function?
Recursive function
It
means the
calls
function is
by
calling
itself.
itself.
Right. So which calls by itself is called as recursive function. And let me give you a quick question here. Class. Can you tell me what is the output for this particular code or for this particular recursive method?
That this will be infinite. You should have a break or the condition so that it can exit the method.
Right. So this should throw us an memory error because we are keep on adding the calls to our stack. So basically the error is something like this: stack overflow. So whenever we are calling, we are using recursive functions, you need to make sure that it has a break, or else it is gonna throw us stack overflow error, right? So this is something, this is the first point that you need to make a note. What is stack overflow error when you're gonna encounter that? So the next is, I have something like this: sys out after my first recursion call. Can you say me what? Or let me put something here.
It won't be printed because before it calls the print, it just keeps going.
No, let me add some break for this by using some
Okay.
count b is greater than 3. Jam. Count is equal to count plus 1. And pass it here.
You have to give it.
Can you tell me what is the output for this? What will be the output for this? Let me take you a note. So please predict the output so that I can write it here if you want me to write.
I think it will be just printed once.
It will
Like,
print only once. So your answer is after my first recursion call will be printed only once, right?
yeah.
Okay. So the first answer I got is this one. So it will print, this will get printed only once. Control V.
I think it looks like we'll get the count one first time, then it will count will go in the method one, then it will go on the recursive method again, and it will call this time one, then it will come in the method, then it will be two, then it will go for the three. So it will print three times, I think, because three so, because 3 is greater than 3, no. When it will go for
I think it will print twice, not once. Sorry, Liquid.
So it will print twice.
Yeah.
So someone is saying
uh,
something.
Suman was telling, I think Suman, she's
yeah,
saying three
I think
times.
it will go because we are checking count is greater than 3, then it will return. So it keep on going in the recursive method.
Okay. So,
First time 1, then second time it will be 2 because count plus 1 equal to 2. So count is 1, so 1 plus 1 equal to 2.
so what is the end output? Can you say me that? How many times this will get
Sir,
printed?
I think it will print like 4 times because like for 0 it will
Four
print first it
times.
is returning. For 1 it will print. After like 4,
1, 2,
when
3.
the count is 4 greater than 3, uh,
It returns.
for, yeah, it will print for 4, 0 to 3, so 4 times.
Yeah.
4 times. Okay. So
Yeah.
any other answers from any others?
It will print 3 times.
3 times is one. So 2 times, 4 times, 3 times. Any other answers?
Maybe 3 times.
3 times. Okay. Let's execute this and see the output. Run as Java application. Right. So now the right answer is 4 times. Let me explain you this clearly. So this is very important to understand the sorting algorithms. So because we will use this recursive methods frequently in our coming algorithms. So try to understand this carefully. So let me keep a breakpoint here and let me debug this. Run as Java application. So now I am here, and also let me watch this value, which is count. So now I am stepping into this. So look at the stack as well. So now from the main function, we call recursive method, right? Now we are at line number 13. So now I'm switching. Now the count value is 0. 0 greater than 3 is true. and now I'm going to my next step, and my stack is at line number 16, right? I'm at line number 16 now, so I'm switching, I'm executing this. So now my count is 1, and then I'm calling this method again recursively, and the parameter now is 1, right? So now I need to have another line that is added to my stack. So this is pending from 17, 18 is pending to get executed in this call. In this particular stack call, we executed still line number 17, and we have a pending line that needs to be executed at, and this is pending, and this will be executed once this call is completed. What is this call? This call is again to execute this method. So another stack line or stack frame will be created. If you see this got stopped, this particular stack call got stopped at line number 17, and it is still pending to execute line number 18. When this will be executed? Once this particular method got executed. So it is waiting for this particular call to get completed, and then only it will do the execution of this particular line. So this particular stack frame will execute line number 18 only once it completes this particular call. This call is for this same function. So now we are at line number 13 of the same method, recursive method. So now this will keep on going. So now this call is to execute this whole function again, right? So now let me do that again. So now we reach to line number 17 of this particular stack frame, and now the count is 2. You can see the count here as 2, and now the call is again to execute this method. For this stack frame as well, this particular line is pending, and this particular line will be executed only if it completes this line. This line is calling another method or the same method with the same name, or the recursive method. So again the call is for to execute the same method. It need to complete this method to go and execute this particular line. So now you can conclude that for this stack frame we have 18 line pending with us, and for this stack frame as well we have 18 line pending with us. And now if I step in, now again the call is went to this same method, and now the count is 2, and 2 is greater than 3 is true. 2 is greater than 3 is not true, it is false. So it didn't went into this if loop, and now the count is getting increased. And now again we reached line number 17, and so it will not execute line number 18 until this completes this particular call or this particular method. So if I step into this, so we have 4 stack frames with the same name, and these 3 stack frames have 18 line pending for execution. So it is doing the execution of this line itself. So once this is completed, it will call the 18th line. Okay, so it has to complete its 18th line, this stack frame, because this is the last call. So this is the first that will get executed. So once the 18th line of this gets executed, the 18th line of this will be executed, and then 18th line of this will be executed. So that is the sequential order. It should be in reverse order, because the first stack frame will be executed first, and then the next stack frame, and then the next stack frame. So now in this we have it's another stack frame call, and we are at line number 13. So if I switch into this, I'm incrementing my count now. My count is 4 now, and again this stack frame will have 18th line pending because it has a method call again. So if I step into, there will be another stack frame that will be added because it is a method call or the recursive call we have. And now 4 greater than 3 is false, and it will come out of this particular method. So this particular stack frame will end at line number 13 itself. It doesn't execute these 3 statements because we have a return statement here, and this return statement will be executed as 4 is greater than 3. So if I step into this, I have a return. So this stack frame will be popped out. So if I press enter, so this got popped out, and the next stack frame's 18th line is getting executed now. So this is the last stack frame that called 17th line, and it went into recursive, went into this call as the count is greater than 3. That stack frame got popped out, and now the 18th line of this particular stack frame is getting executed. So now if I step in, oh, step out. Now if you see, in this particular stack frame we executed line number 18 and we are at line number 20. So once it is done, that got popped out because we completed the execution of that particular stack frame or that particular method call. So now we are at this particular point. This is for this stack frame. In the similar manner, once this is completed, this will be popped out and it will reach the 18th line of this line. So once this particular stack frame completes its execution, we will go to this particular stack frame and we will do the execution for the 18th and 20th lines that we have for this method call. So let's see carefully what is happening. So we printed the first recursion call, and then one really slow. So that got popped out and we reached to the 18th line of the next stack frame. So now if I step so that got popped out and we reached to the 20th line. I mean, we are at 20th line, and once we execute this, that stack frame will be popped out. So now we are at last stack frame or the first method call that we have done, and it will print this line, and it's at 20th line. So everything is done. The main thread will be exited and the other daemon threads will be executed, and it will close everything. So that is how a recursive function has to be debugged, and that these are all the observations that you need to make. What is the stack frame calls, what are the how the outputs are changing, how the outputs are increasing, and what will be the output. So everyone got this?
Yes, sir.
Yes, sir.
Okay, so say me the output for this then. So I'm adding something called as count here, control S. So what will be the output now?
It will be in reverse order because the in stack it is popping like 4, 3, 2, 1. So like that it will show.
Okay, so you're saying the output is 4, 3, 2, 1, right? Control C. 4, 3, 2, 1. This is what you're saying, right?
Yes, sir. Because there are four. Yeah.
Okay. So any other answers?
No, sir. I think it will be 4, 3, 2, 1.
I'll go with him, sir. Yeah, that's the right output.
Right. So let's execute this. Run as Java application. So the prediction is right. We have 4, 3, 2, 1. So why it is 4, 3, 2, 1? In the first, let me execute this again so that you will get it clear. Run as Java application. So debug as Java application. Switch. Let me do this regression. This is just to show you how to see the values for multiple stack frames. I'm just doing that. So debug as Java application. Now I'm here.
It's because like the condition Yeah.
So for this, in this stack frame, what is the count value? It is 1. So when the 18th line of this particular stack frame is getting executed, the count value will be 1. That's why as the 18th line of this stack frame will be executed at the end, right? So once all the lines of this stack frames got executed, then it comes to this particular stack frame, and for this stack frame the 18th line will be executed at the last. So the count value in this particular stack frame is 1. So if you go to the next stack frame, the above stack frame, so in this stack frame it has a call to this method recursively, but the count value is stored as 2 for that particular round of regression, or I mean for that particular round of execution. The count value in this stack frame is 2. If you see this particular stack frame, count value will be 3 for this stack frame and count value will be 4 for this stack frame. So that's the reason uh, this stack frame is printed count as 3 when it is executing its line. So this stack frame printed count as 2 when this is executing this particular line. So this stack frame printed 1. So you can see the variable values of different stack frames by just clicking that, and you can see the variable values over here. So for the first stack frame the value is 1, for the second stack frame the value is 2. So the second stack frame stopped at 17th line. Once all the stack frames above it are completed their execution, this will resume its execution, and it will start its execution from the 18th line. So when it is starting its execution from 18th line, it's trying to print the value of count, which is 2. That you can find out here. So the count is 2 for the stack frame 2. So that will be printed. Why the count is 2 here? At 2 it called recursively to the another method call. So the count is stored as 2 and it will be kept aside. So another stack frame will be created, and there the count value will be changed to 3, but not in this stack frame. In this stack frame the value for the count is stored as 2, so it will preserve that until it completes its execution. So every stack frame, the takeaway here is like every stack frame will store the values of its variables at that state. It will not change the values based on the current regression cycles or current stack frames. As it is, as a count value got changed to 3 here, it will not update the value as 3 in this stack frame. It is independent, and it is independent. The variable values in this stack frame is independent, and in this stack frame is independent. That is something that needs to be understood here. So that is the reason the output is this way. Now let me put it this way. I'm doing another recursion call here. Boom. After my second recursion call, so yes. Can someone predict the value of this? What will be the output for this? Or else someone of you can copy this code into your machine directly. I'm just pasting it in the conversation, so you can explain to us as well. You cannot predict this directly, but I recommend you to put this in your Eclipse and explain us how the execution flow is going. I mean how this will work and what will be the output. Where is the conversation? Oh, can someone ping some message in the conversation? I'm not able to find that. So that I'll try to paste this code there, and you can pick that and you can paste it in your. Thanks, Ramya. So I'm just pasting this code here. So I gave the code over there. So you can copy the same and you can try to explain that piece of code. I mean, how this recursive calls will happen for that particular function and what will be the output for this recursion code.
So it's printing 1, 2, 3, 4, and then again 4, 3, 2, 1.
Mm-hmm.
So before calling the recursive method, the value is printed. So first it's incremented and the value is printed. So we pass it 0. So it is incremented and the value is printed as 1. Again, the recursive method is called and again it goes inside and the
Shivagam, if possible, can you share your screen and explain to everyone like how the recursive calls are getting and how the output is getting printed?
okay, I think it's shared now. So here the code is like when the recursive method is called, it is incremented, the count is incremented and it is printed 1. So again the recursive method is called here. So again it goes back and it increments the value.
Shivagami, can you just show in the debug mode?
I don't know, I was trying to debug some time back. I couldn't do it. So let me try one more time.
Need to put break. Okay.
Like when you click it here, it has to come, right? How do you add a breakpoint? Like when you click on the line number, it has to come.
Yeah. That's how we put it.
Yeah, but I don't know, it was not happening. I tried some time back.
So your debug is disabled. I mean, debugging option is disabled. So you need to enable that. The option will be at. Where is the debugging? Can you quickly Google where to enable debugging in Eclipse? You can find an option there. It will be somewhere. Or else, if some other can share the screen and show us, it
Yeah,
would
I
be
think
better, I
it's,
guess.
I think if somebody's ready, they can show.
Any others are ready to explain this? So maybe if some others can take this, they can do the they can explain that, or if you want me to do that, I can do that as well. Hello, anyone wants to do this? Okay, right. So let me debug this. Let me show you. So right click, debug as Java application. So right now I'm here. So count is 0, count is incremented, and here is the recursion call. So stack frame switch to line number 13, and again it's doing a recursion call here. Now it's again doing a recursion call. The count value is 3 and it got incremented, so it's again doing a recursion call. So there are 4 recursion calls happen for the from the line number 17. So now 4 is greater than
Sir, I think
this.
video is paused.
It's paused. Able to see my screen now?
Yes, sir.
Okay. So do you want me to execute again, or is this fine?
Just explanation is fine, sir.
Okay. So we from here, from line number 7 we came to line number 17, and recursion call has done, and the value of count is 1 here. So because of that recursive call, we another stack frame is created, and again at line number 17 it has done a recursion call, and the count value for this particular stack frame is 2, and this is the third stack frame, and this is the third stack frame. All these calls are being done by this recursive method, the first recursive method call at line number 17. And now we are at line number 13, and the count is 4 is greater than 3, so that this stack frame has to be popped up now, popped out. So if I step into and a return is called on this, so this will be popped out, and now this stack frame's 18th line will be called. So right, so this stack frames 18th line is called. Now we have 4 stack frames, and now this stack frames 18th line call is in progress. So now it will print this value, and the count of the stack frame will be 4. So the output is, oh, so the output now is, after my first recursive call, 4. Now this is again a recursive call, and for this stack frame the line is pending at 19th. So here there is a recursive call happening again. So what is the count here? So count is 4. So you understood, right, how the count became 4 here? So that is one of the important things that you need to understood.
Yes, sir.
Why? Because this, from this stack frame we are doing this call, right? In this stack frame the count is 4, so the same applies for this particular recursive call as well. So as we are here, so the count is 4. So if this stack frame is executing line number 19, the count value will be equal to 3, because this stack frame has count value as 3. If this particular stack frame is calling this method, the count will be passed as 2. If this stack frame is doing it, the count value will be passed as 1. So as we are on the last stack frame, and in this stack frame the value of count is 4, so as it is calling this recursive method now, the value of the count will be 4, and 4 is greater than 3 is something true, and it will return the function, so that this stack will be popped out. So I am stepping into now, and we're calling a return, so that this stack frame's 19th line got executed, and that particular stack frame which got created is popped out because 4 is greater than 3. And now the last line of this particular stack frame will be executed. And so if I step over this, so it called this particular recursive function, and now it will end up here, and this stack frame will be popped out. So I'm stepping over again. So now this stack frame's 18th line is called now. So if you hover this, count value will be 3, and now it is calling this recursive function again, and the value is 3, and now it will go to this recursive call, and another stack frame will be created, and this stack frame execution started from 13. So the count value is 3 here, 3 is greater than 3 is false, so it will come down, count will be incremented, and then again a recursive call will be made, and the value of the count will be equal to 4 now as it is incremented. So now again another stack frame will be created, and the execution will be started from 13th line. So 4 is greater than 3, so it is true, and return will be called, so that this stack frame will be popped out. So I'm just executing this, so this is popped out. So now we are at now line number 18 of this stack frame. So it goes on, and finally you can do the debugging in this way, and if you execute this, the final output will be something like this. 4 4 3 4 4 3 2 4 4 3 4 4 3 2. How random this is, and how many calls this has happened. Have a look at this. And this the same kind of recursion we are going to use in some of our sorting techniques. So that's the reason I explained you this, but it is very important for you to understand this recursive functions when you're calling it multiple times in the same method. So the same logic, the same kind of logic we will use in our sorting algorithms. Inside a single recursive method, inside a method, we will call that recursively twice. So this will be used over there, so you need to understand this carefully by debugging this. So the whole point here is like you has to be able to write the output by just seeing the code without debugging as well. That is very important. You try this once this session is over. You can try this at your home. You don't debug this, you put this code on your book or paper, and then try to get the output, and then match the output that you have written on the paper to the output that is coming in the IDE. So you compare both of them, and check whether you're doing it right, you understood it right or not. So go line by line. So if there is any recursive call, write it over there. So this is the recursive call for this, and here is my stack, and once this is popped out, the call will come here. So that's how you need to debug this on paper. So you need to put it everything, and you need to also put the count variable counts and everything. So what are important parameters that we found here? One is the stack frame, and the other one is variable values. So you write those by on your own on paper as well, and make sure you are getting the right output. So try this on paper, not on IDE first, and then come to your IDE, execute that code, and check your output on your paper to the IDE. So both should match. So if both are matching, your understanding is correct, and you are clear with this. So if you're not able to understand this, it would be messy for you when you are. We'll use this recursive method in one of our sorting algorithms called as merge sort. So in that sorting, we will call multiple recursive calls. So if you're not able to understand this, that is more complex than this, because we will have multiple variables over there. So that will be complex if you don't understand this. If we have single variable here, there will have two variables. Using those two variables, we will implement that recursive method over there. So it is very important for you to understand this. And as I told you, you try to put this on paper and try to get this output on the paper, and then run it on the IDE and try to compare both the outputs. So that is the better way to learn this recursive methods. This is all about recursive functions, and then now we can move forward to sorting algorithms. After this, still now we learn what is big O notation, what is space complexity, what is time complexity, and how a big O complexity chart looks like, and what is recursion, and how a recursion works, how the stack frame calls will be, how the variable values will be in different stack frames, and what happens if multiple recursion calls are being done in the same method, and all the stuffs we have learned till now, and these all will be useful in our further lectures. For example, we have sorting algorithms, and we have multiple sorting algorithms for us, and different sorting algorithms will have different time complexities, and you should be able to calculate the time complexities based on the learnings that we have done till now. And if I give the code for you, you should be able to calculate the time complexity for that particular algorithm, and that is one part. And based on the time complexities for different algorithms, you can decide which algorithm has to be used for mm, uh, which algorithm has to be used. Obviously the algorithm which has less time complexity should be used. For example, I have two algorithms with order of n square and order of n log n, so you need to go for order of n log n. And even if your interviewer is asking some questions like if he wants you to sort an algorithm, so the next question that you need to ask is, what is the priority for you? Is the time complexity or the space complexity? If he is saying space complexity, you need to choose an algorithm which has less time complexity. So if he's asking about less time complexity, you need to choose an algorithm saying which has less time complexity. For example, I have algorithm 1 and algorithm 2. Algorithm 1 has less time complexity but more space complexity, and the algorithm 2 has more time complexity and less space complexity. So the moment the interviewer is asking you about write a logic to implement the sorting of an algorithm, so you need to ask him what is the priority here, is the time complexity or the space complexity. Once you put that question to the interviewer, he'll come to know that you are very well versed with algorithms and time complex and space complexity, so that he gets an idea that you are aware of data structures as well. So simply writing two for loops and getting it sorted is not something that is feasible, but putting a question saying what is important here, is the time complexity or space complexity, and then it's an hint for him saying that I also know the data structures very clearly. So when once he chooses time complexity as the major criteria, you can pick algorithm 2, and if he chooses space complexity as the highest criteria, you can choose algorithm, and you can put that on paper. So coming to this algorithm things, you doesn't need to really remember the code, and the code is readily available on Google. But the only thing that you need to do, that you need to know, is you need to understand the code. You need to understand the logic of different algorithms. That's the whole concept that we will learn here. And the other takeaway from these lectures will be, so you will come to know what algorithm has to be used for which kind of scenarios. As I told, if the time complexity is major for your applications, you will come to know what algorithm has to be used, or what sorting technology has to be used to sort them. So these all things you'll know once you're done with these lectures. So in class, we are gonna discuss four sorting algorithms. I'll show you by debugging each and every algorithm, and I'll also show you how the sorting works, and what are the different methodologies that will be followed, and in each and every sorting algorithms. And later you can practice few of the sorting algorithms, and you can come out with space complexity and time complexity, and you can decide which algorithm has to be picked at what kind of scenarios. So still now, I hope everything is clear for everyone. So you know how to calculate time complexity and space complexity for different kinds of codes, and you also know how the recursive calls and recursive methods work. So these are two very important prerequisites to start our sorting techniques or sorting algorithms. So hope everyone is clear with them. If you have any queries, we will wind them right away, and then we will move forward to sorting techniques. So do anyone have any questions in these two topics?
No, sir.
So everyone is clear with this, right? But I recommend strongly to every one of you that you need to put this on paper and you need to try to get this output on the paper and then come back to IDE so that you will be clear with this recursion topic. And then when I'm so the other sortings, bubble, insertion, selection sortings, logics are very simple. But and coming to merge sort implementation, this particular recursive is very important because it all depends on this. So that's why I'm strongly I'm just repeating this again and again. And so let's wind off this here. Let's move back to our sorting techniques. So let's come to the sorting, or like keeping or tracking the numbers in an ascending order or descending order, or modifying the numbers into descending or ascending order. That is what we all know what is sorting is. And let's study different sorting techniques one after the other. So the first sorting technique is bubble sort. The first sorting technique is bubble sort that we are going to discuss today. Bubble sort is the first one that we are going to discuss. So please give me a minute. So the first sorting technique is bubble sort. So how basically this works is uh, so the first sorting technique is bubble sort, and let's look at how this is implemented and how this logic basically works. Let me say I have an array of 12, 20, 11, 5, minus 5, 2, and
Sir, we are not able to see your screen.
okay. Is it visible now?
Yes, sir.
Okay. So basically how this works is, so this is the array that is given to us, and we need to develop an algorithm to sort these elements. So how bubble sort works is, so basically it will compare each and every element to the other element. So it will, in the first round of iteration, in the first round of iteration, this I'll call this as first iteration. what basically happens is, so 20 will be compared with 11. So it will start iterating from this first element, 0th index element, to the last index element of this array. So in all these elements, it will have its I over here. So it will have I declared here. So the I index will be here initially. So I will be here. So this is I. So now from I is equal to 0, I less than array dot length minus 1 I plus plus. So that is the inner loop. Inside this inner loop, what basically happens is, it will compare the index of 20th with index of plus 1 I plus 1. So it will compare 20 is greater than 11 or not. So if it is greater than 11, if index of I is greater than index of I plus 1, so it will swap those elements. If not, it will keep them same. It will not swap the elements over there. As 20 is greater than 11, it will move the elements, it will swap the elements. So next, the new elements, I mean to say, new set of elements after swapping the elements in the first round of iteration is, it will be 11, 20, 5, minus 5, and 2 and 7. So this is the first iteration. So in the second iteration, the index will be moved to 20. The index will be incremented by 1. So now the index will be pointed to 20. So now this will be compared with the next element. 20 is greater than 5 or not. So as 20 is greater than 5, the next set of elements, or the next set of array elements, will be equal to 11, it is 11, 5, 20, minus 5, 2 and 7. So now the I is at this index. Now I is at this index. Now I is at this index. Now we need to increment the I to the next index. So it is my here is my I, and now I need to compare the I with I plus 1 element. So now you need to compare 20 is greater than minus 5 or not. It is true, 20 is greater than minus 5. So the next set of output will be something like this. It is 11, 5, minus 5. We need to swap. If the condition is satisfied, if a of I is greater than a of I plus 1, if a of I is greater than a of I plus 1, we need to swap the elements. If a of I is greater than a of I plus 1, we need to swap the elements. A of I, we need to swap the elements. Here we need to iterate through the entire loop. For I is equal to 0 to, for I is equal to 0 to I greater than, I less than array dot length minus 1 I plus plus. I plus plus. This is what we are basically doing. So once this is satisfied, if a of I is greater than a of I plus 1, we need to swap the elements. Swap the elements. This is all that we are doing in this bubble sort, right? So we started from index 0, and we are comparing the element at index 0 to index of 1. 0 plus 1 is 1. If both, or if an element at index 0 is greater than element at 1, we are swapping the elements. That is what we have done here. Again, we are incrementing the I. So earlier it is at 0, now it is at 1. So a of 1 is compared with a of 2. So as a of 1 is greater than a of I plus 1, we swap the elements. 25 is swapped with 20. Now again, we need to swap. We need to check I is incremented to 2. So 20 is greater than minus 5 or not. So it is greater than minus 5. So it is, now it is 11, 5, minus 5, 20, 2 and 7. And in the next round, the I will be here. As I is incremented, I will be here. So what is the output here? So in the next round, the output will be 11, 5, minus 5, 2 and 20 and 7. So because I is here, 20 is greater than 2, so we need to swap elements. At last, here the output will be 11, 5, minus 5, 2, 7 and 20, right? So this is my first iteration, and I completed iterating the length, array dot length minus 1 times. So my final output after first round of iteration of the inner loop is 11, 5, minus 5, 2, 7, 20. If you carefully observe, the highest number in the particular array is moved to the end, right? So 20 is the highest element in this array and it is moved to the end after first round of iteration. So after completing one round of iteration of this inner loop, we completed we moved the highest element highest element in this array to the end. So now what we need to do is, the next is we have something called as outer loop, and outer loop structure looks like this. So outer loop is for I is equal to array dot length minus 1, and then if it is greater than or equal to 0, I plus plus. So this is my outer loop. So let's not call this as I, let's put this as j greater than 0 and j plus plus. So now I'll keep like this, I is less than j. So here my logic is I less than j. So this is my logic. Initially j's length is same, array dot length minus 1. So now, so it is j minus minus. Yes, someone is asking something.
Yeah, Mohan.
Yeah,
So it could be like a j equal to 0 and j is less than equal to length and j plus plus. In this case, it should be j minus minus, right?
yeah, j minus minus. I wrote it wrongly, I'm correcting that. So you're saying this one only, right? J minus minus.
Yeah, yeah.
Yeah, I'm correcting that. I just told that. So this should be j minus minus. So earlier what we have done, so we compared the entire array. Now the j value, the outer loop j is decremented, and we are iterating the inner loop only still here, not to the last element. So we are iterating only still here. So j minus 1 times we are iterating. So we are excluding 20, and as 20 is the highest element in the array, it is moved to the end. So whatever the highest element that we have in the array, that will be moved to the end by end of the first iteration of the inner loop. So now the same logic will be repeated for the rest of the elements, leaving the last element. See, the for the outer loop, the initialization is j is equal to array dot length minus 1, and we are checking the conditions, and at the end we are decrementing the value of j. So earlier the index of j is this array dot length minus 1. Now the j is something here, and now we want to iterate the I still here, not more than this. So I is iterated from 0 to j. J is something j minus 1 or array dot length minus 2. Now the same logic will be repeated. So I starts from 0. So what I starts at 0, it compares its value with 11 greater than 5 or not. As 11 is greater than 5, so the next set of output in the second round of iteration is, this is second round of iteration I am doing. So this is second round of iteration. So the output here will be, so I started at index 0 and it is comparing its value with the I plus 1 value. So 11 is greater than 5, so output will be 5, 11 minus 5, 2 and 7, and this is 20. This is common. So the next is, the I will be here at index 2. The I will be at index 2 now. So it will compare with 11 greater than 5 or not. It is true. So 5, it is minus 5, and 11, 2 and 7 and 20. So index will be moved to here. So the next output will be 5 and minus 5 and 2 and 11 and 7 and 20, right? So the next output will be, hope every one of you are getting this. I'm just directly writing the output now. 7, 11 and 20. Everyone got this? We moved the second highest element to the end now. So we have the first highest element at the end in the first iteration. In the second round of iteration, we move the second highest element to the end. So now the j will be decremented and the barrier comes to here. So now we are gonna iterate the I loop only still here. We are not no more consider 11 and 20 for our sorting purpose, because these two values are already sorted and moved to the end. Everyone got this?
Yes, sir.
Yes. So it is moved. Now we have only 4 elements that we need to iterate and we need to sort. In the third set of iteration, I mean in the third round of iteration, what basically happens? Can someone tell me the output for the third round of iteration? So so this is the array I have in the start of third round of iteration. So what is the next output?
Minus 5, 5 to 7, 11, 20.
2, 7, 11 and 20. Right. What's the next?
Minus 5, 2, 5, 7, 11, 20.
2, 5, 7, 11 and 20. So what's the next? Minus 5, 2, 5. So that's all right. So this ends, it ends here.
It's sorted. Yeah.
It's all. It's fine. So let's consider this here. So it is started still here. So hope everyone understood this. So in the next round of iteration, there is nothing. Minus 5 is greater than 2 is false. So it will not swap these two numbers. 2 is greater than 5 is false. It will not swap these numbers. So now it is done. The j will be decremented here. So minus 5 is greater than 2 or not is the next iteration. It is not true. So it will not swap the elements and the barrier comes here. And the last element is this one, minus 5. So in this way, the bubble sort will sort the elements. This is the logic that the bubble sort uses to sort the array elements. Okay, so now can you say me the time complexity of this?
O of n square.
Perfect. It is O of n square. Why?
Like outer loop and inner loop, inside a loop, one inside other
So
loop.
this loop is iterating n times, and for each and every iteration of this particular outer loop, it is iterating for n times. So this it will iterate n times, and for each time of this outer loop, the inner loop is iterating for n times. So it is n into n. That is why it is order of n square. So the time complexity of bubble sort is order of n square. And what is the space complexity?
Of a or one, like what do
Yeah,
they say?
it is constant. So O of 1 or
Yeah,
a.
constant. Yeah.
So this is constant time complexity. So the space complexity. So time complexity of this logic is order of n square, whereas the space complexity is order of 1. Okay, this is all about bubble sort, and I hope every one of you can implement this on paper. I hope so, or else, do you want me to explain the code or can you do it on your own?
We can try it, I think.
Yes, please try it. So it's very simple. This is the same. You need to write two loops. The outer loop should start from j is equal to something like this. So where is that? Here it is. So it should start, the outer loop is something like this: j is equal to array dot length minus 1, j greater than 0, j minus minus, and the inner loop starts from I is equal to 0, I less than j, I plus plus, and just swap the elements. You know the logic to swap the elements. It's simple. Take a temp variable and pass the old value to it, and the new value to this variable, and temp value to that variable. So that is something like this. So you know the logic of this swap, right? So declare a variable called as temp and pass the value of a of I, and now pass a of to a of I, pass the value of a of I plus 1, and then to a of I plus 1, pass temp. Can you say me any other logic for swapping other than this?
Yeah, sir, we can like take one variable, like temporary variable, swap. If swap is not equal to 0, then it will iterate. Here we are checking for -5, 2, and 5, even if it is like shorted. So when the swap found like there is no swapping left, then it will stop there only.
No. I'm asking, like, this is the condition that decides whether we need to swap or not, right? So that is different. So
Yeah,
this is one logic to swap, right? So
yeah.
to swap two numbers, this is one logic. So I have two variables a and b. You might be aware, I'm just repeating. So I have two values a and b. So I need to put the value of b into a and the value of a to b. So what I'm doing, so I need to keep the value of a into a temp variable. So let's say I have 3 in this and 2 in this. So in a, let's say I have 3 and I have 2 in b. So what I'm doing, I need to swap both the numbers. Now I am putting the value of a into a temp variable, and then I am passing the value of b into a. So a is equal to b, so I'm passing the value of a into b. So now my a has value 2. Now into b, I'm passing my temp variable, which is 3. This is one way of implementing the swap, right? I'm asking, can you tell me any other way to swap the numbers other than this logic? So I want you to tell some other logic to do the swap.
Sir, you can add, subtract, and that is the
Right.
other way.
Yeah,
Like
that is
you
the other way
can,
to do it.
yeah.
So a is equal to a plus b, and once it is added, and then we need to minus, and then we need to minus the other variable, and we need to pass this to the second variable. So adding this two numbers and minusing the other number will give the, I mean to say, we'll swap the numbers, adding and then subtracting. That is the other logic we have. A is equal to a plus b or something, so that you can develop. So that comes with two lines, and we doesn't need to have the third variable that is stored. So here the space complexity is attained with temp variable. In that case, we doesn't need to have the space complexity as well. We don't have any space complexity for that logic. So that is one logic that we can write for swapping the numbers. Okay. So this is the bubble sort, and this is the implementation for that. If you want me to keep this on Eclipse, you can do it tomorrow, but you try to do it on your own. So it's very simple. That is the first sorting technique, which is bubble sort, and the second sorting technique is selection sort. So how selection sort basically happens is, it's very simple like bubble sort. So it is just, so the second one is selection sort, is the second one. Let's take the same array, something like, now no 6, 20, -2, 11, 56, and 5. So this is the array that is given to us, and we need to sort this using selection sort. So here what basically happens is, here basically what we will do is, we will take a variable called as largest element or something. So we are taking a largest element and we are assigning it with 0. Then The inner loop for this will be something like this. So inner loop is for I is equal to 1, I less than array dot length minus 1 and I plus plus and I plus plus array dot length minus I plus plus. So this is the inner loop, and inside this inner loop we have an if condition. Inside this inner loop we have an if condition. So if condition says array dot array of I, or something like this, array of I if this is greater than int so let's say its largest element. So this is largest element I have. If array of I is greater than largest element, so just so the whole concept in selection sort is, let me explain this before. So we need to pick the largest element in this array. We need to pick the index of the largest element, and then we need to move that largest element to the end. So here the largest element is 56, and we need to get the index of this, and then we need to move this index this element to the end. So in the first round of iteration this happens. It is 6, 20, minus 2 and 11. So after completing one round of iteration, we will notice what is the highest element. So we pick the highest element as 56, and the index of this as array of array dot length minus 2, or else let me put this way, 0, 1, 2, 3, 4. So the highest element is found at index 4. Now we need to swap the last element with this element. So after swapping, so it will be like 56. So the whole concept here is like we need to fetch the highest element index and then swap the index of the highest element with the last element. So whatever element that is there here, that will be moved to this location, and the highest element found index will be moved to the last location. So once that is done, we will decrement that again. So now we will put a barrier here. So now we will put something, a barrier here, and then we will start iterating until here only. So we will not iterate still array dot length minus 1. Instead we will iterate only still here. So now what happens, I is equal to 0 to I less than j. So j comes still here. So we will iterate through all the loop and we will find the index of the highest element. So finding the index of the highest element is highest element is at index 1. So we will swap the elements at index 1 with the last index, that is array of j minus length minus 1. So the next value or next sorted iteration will be something like this. It will be 6, 2, minus 20, minus 2, 11 and 20 and 56, because we are swapping these two elements. So swapping in the sense, so this is the highest element, and it is found at index 2. So the highest index has to be swapped with the array dot length minus 1, because the j value is at here, the outer loop is at here. So outer loop will be same for j is equal to array dot length minus 1 if j is greater than or equal to 0, and j minus minus, so it is decremented here. Now we need to swap array of the largest found index with this index. So now the value will be something like this. It is
Sir,
6,
it's
5.
not 2, it is
Yeah, it is
5.
5. So 6, 5, minus 2, 11, 20 and 56. Now the barrier comes here. Now we are going to compare only the first 4 elements, and the highest element is found at index end. So we doesn't really need to swap. Even if we swap, the same happens. So now the barrier comes here. So the now it will fetch the highest element. The highest element is found at index 0. So we need to swap these two elements now. So the output now will be equal to 2 minus 2 and 5 and 6 and 11 and 20 and 56. So what now the barrier comes here, right? So it will be at 5. So it will try to fetch the highest element. Highest element is found at the last index, so we don't need to bother, or we don't need to swap. Even if you swap, nothing happens. So the barrier comes here and it's end. So the element is now sorted, the array is now sorted. And here it's similar to the bubble sort. Instead of moving the highest element to the end on the go, we are just fetching the index of that and we are swapping the elements at once. So in bubble sort we are swapping multiple times, right? So we are swapping for each and every iteration, but here what we are doing, we are swapping only once, but we are trying to fetch the index of the highest element and then we are swapping at the end. In the bubble sort it is not something like that. If 20 is greater than minus 2, we swap this. 20 is greater than 11, we swap them. 20 is greater than 5, we swap them. So we are swapping them multiple times in bubble sort. So that is reduced here, the swapping operation is reduced, and here we are swapping only once by fetching the index of the highest element. And that is what we are doing here. So let's say how to implement this is something that we need to know. So we know the outer loop is something like this, right? So outer loop will be the same. Outer loop will be for int j is equal to array dot length minus 1, array dot length minus 1. And so the condition for the j is j should be greater than or equal to 0, or let's say greater than 0 j minus minus. Because if we are keeping equal to 0 or not equal to 0, the last element we doesn't really need to bother, because the last element will be the shortest element. It will come at first. If you are doing until the second element, that is fine. The last element will by default will be the smallest element. That's why it came here, right? Or else you can also add equal to 0, but another loop will be added. I mean, it will iterate for another one time. That doesn't matter for the complexities. It can be any number of times. Until unless we'll add an for loop inside for loop, it doesn't matter. It can iterate any number of times, so it doesn't affect our complexity. So you can add 0 equal to 0, or you can exclude that. That's up to you, but it is not needed. The last iteration is not needed. So inside this, what we are going to do is, we are declaring an element int largest is equal to 0. Let me write the complete code and then I'll explain you. Int I is equal to 1, I less than last unsorted index, or it is j here. Now we need to remove this array dot length minus 1, and we need to replace this with j. So we need to remove this now. Delete. So instead of this array dot length minus 1, now I'm gonna keep j. So here comes the j, because we need to keep a barrier at the end. So we are keeping barriers, right? So we doesn't need to iterate through all the elements, as the largest element is already swapped to the end. So this is j here, and inside this element we have something called as int array of I. This array of I is greater than, so array of I is greater than largest. This is the index. So here comes, instead of this, we need to keep array of largest. If this is true, let me erase this completely. So here comes array of largest. Largest is something the index of the element. So instead this, if array of I is greater than array of largest, so we are replacing the largest with I. So this is the inside loop logic. So here if you carefully observe what we are doing, we are iterating through the entire loop and we are checking. Initially we assign the largest index to 0. So the largest index is at here. So now we are iterating through the entire array of elements and we are saying if 6 is greater than 20. So if array of I is greater than 26 is greater than 20, it is not true. So we are not doing anything inside the if loop and then we are moving incrementing the index of I. If you are checking 20 is greater than 2 or not, so 20 is greater than minus 2 is true. So sorry, uh, right. So initially it's 0, array of 0. So array of I starts at 1. So we are comparing 20 with 6. Is 20 greater than 6? It is true. So largest will be moved to 1. So initially I is 1, so the largest will be 1 now. So largest index stays at this point now. So this is the largest is what I told, and then I incremented the value of I. Now I will be 2. So array of 2 will be minus 2. Minus 2 is greater than 20 is false, so nothing will be happened. So the largest still stays at 2. Now the I incremented the I, so it comes to 11. So 11 is greater than 20 is true or not? It is false. So I'm incrementing the I again. So 56 is greater than 20. It is true. So now the largest is replaced with now the largest index to be replaced and it should be pointed to 56. Now the largest index will be pointed to 56. And now I again incremented the I stays at 5 and A of 5 is greater than 56 is false. So at the end, the largest element is found at index of 4. Now what we need to do, we need to swap the elements at the end. Once this loop is done, we need to swap the elements here. So swapping is something swap, and inside this I need to give this, I need to pass the array and the index, so largest index that I found and the index of this particular j, or else I can also pass j. So j is at this point now. So j is at the end, j is pointing to the end element, so I need to swap the element at this index to the largest last element. Now we have kept a barrier and we have come to 4. J is equal to 4 now. So in these 4 elements again we are initializing largest to 0. So largest is of 0 is here. So we are comparing 20 is greater than 0 or not. It is true. So index largest will be pointed to 1 again. So minus 2 is greater than 20 or not? It's false. 11 is greater than 20 or not? False. So 5 is greater than 20 or not? False. So largest element is found at index 1. So we need to swap these two elements now. So this will be swapped with this, and so the largest will be found at 1, j is at 5. So because the outer loop is at 5, so we need to swap here. So we are not swapping at for each and every element, instead we are swapping at the end, and inside the in the inner for loop we are just getting the index of the largest element. So this is how the sorting works, fetching the largest element and then swap the largest element with the last element in the the index of the outer loop. That is how the selection sort will work. Hope everyone got this.
Yes, sir.
Is everyone clear with this?
Yes, sir.
Yeah.
Yes,
So
sir.
in the tomorrow's session, you can try the implementations of both of them, like bubble sort and selection sort. And the insertion sort is something that is similar to these sorting techniques. So come up with so implement bubble sort, selection sort, bubble sort, and also selection sort, and also something called as insertion sort. So try to implement these two logics, bubble sort and selection sort, and also try to study this insertion sort. And all these three sortings has to be demoed tomorrow in the first half, so that we can move to the other logic techniques. If you see what is the time complexity of this, it is order of n square, right? So the time complexity of this is also n square because there is an inner loop and the outer loop. So the time complexity is order of n square. So we need to fetch some other algorithm which has less time complexity than these sorting techniques. So we will study that tomorrow, but for tomorrow's session you try to understand or implement these three sorting techniques and try to demo them. Maybe I'll try to pick someone from the audience list, and I'll give the presentation access to them, so that they can demo that. So please get yourself ready with these sorting techniques by to for the next session. So that's all from my end, and if you have no questions, you can wind up and you can leave the meeting. Thanks for joining the session.
Thank you, Mohan.
Thank you.
Thank you.